Close your eyes now and let me tell you about an invisible war, a conflict that has raged since the very beginning of human existence, a battle that has shaped your body, your genes, your immune system, and the entire course of human history. This is the story of the diseases that shaped humanity, the plagues and pestilences that killed billions yet made us who we are, the tiny organisms that have been our greatest enemies and, in a strange way, our most powerful sculptors. It is a story written in your DNA, in the antibodies flowing through your blood right now, in the genetic inheritance that protects you from threats your conscious mind has never known. And it is a story that reveals something profound about the relationship between destruction and creation, about how the forces that kill us also make us stronger. You are the descendant of survivors. This is not a metaphor or an inspirational statement, it is a biological fact. Every one of your ancestors, stretching back millions of years, survived long enough to reproduce. They survived predators, famines, accidents, violence, and most importantly, they survived disease. The diseases that killed their siblings, their parents, their children, their neighbours, did not kill them, or at least did not kill them before they passed on their genes. You exist because your ancestors had something, some genetic advantage, some immune response, some lucky mutation that let them survive what others could not. This process of survival and reproduction in the face of disease is natural selection at its most brutal and its most effective. Diseases are selective pressures, forces that favour certain genetic variants over others. When a plague sweeps through a population, those with genetic resistance are more likely to survive, more likely to reproduce, more likely to pass on their resistant genes. Over generations, these genes become more common, and the population becomes more resistant. The diseases shape the population, selecting for certain traits and against others. This shaping has been happening for as long as life has existed. Bacteria have been fighting viruses for billions of years. Single-celled organisms developed the first immune systems, primitive defences against invasion. As life became more complex, so did the diseases that attacked it, and the defences against those diseases. By the time humans appeared, we inherited immune systems that had been refined by hundreds of millions of years of evolutionary warfare. But humans also faced new challenges. As we evolved, as we changed our behaviours and our environments, we encountered new diseases, new pathogens, new threats. The transition from forest to savanna exposed us to different parasites. The development of tools and fire changed our relationship with the microbial world. The invention of agriculture, the domestication of animals, the building of cities, each of these transformations brought new diseases, and each disease shaped humanity in turn. Malaria is ancient. The parasites that cause it have been infecting primates for millions of years, long before humans existed. When our ancestors descended from the trees and began walking across the African savanna, malaria was waiting for them. It has been killing humans ever since. The disease is caused by Plasmodium parasites, single-celled organisms that live part of their life cycle in mosquitoes and part in humans. When an infected mosquito bites you, it injects the parasites into your bloodstream. The parasites travel to your liver, where they multiply, then emerge to infect your red blood cells. Inside the red blood cells, they multiply again, eventually bursting the cells and releasing new parasites to infect more cells. This cycle of infection and destruction causes the characteristic symptoms of malaria: fever, chills, sweating, and in severe cases, organ failure and death. Malaria has killed more humans than any other disease in history. The numbers are almost incomprehensible. Estimates suggest that malaria has killed half of all humans who have ever lived. Even today, with modern medicine, malaria kills hundreds of thousands of people every year, mostly children in sub-Saharan Africa. For most of human history, the death toll was far higher. This relentless killing created intense selective pressure. Individuals with any genetic variant that provided even slight resistance to malaria had a survival advantage. They were more likely to live to adulthood, more likely to reproduce, more likely to pass on their genes. Over thousands of generations, these resistant variants became more common in populations where malaria was endemic. The most famous of these variants is the sickle cell trait. Sickle cell disease is caused by a mutation in the gene for hemoglobin, the protein in red blood cells that carries oxygen. People with 2 copies of the mutated gene have sickle cell disease, a serious condition where red blood cells become misshapen and can block blood vessels, causing pain, organ damage, and shortened lifespan. But people with only one copy of the mutated gene, carriers of the sickle cell trait, have a significant advantage. They are resistant to malaria. The malaria parasite cannot thrive in red blood cells that carry the sickle cell trait. Something about the altered hemoglobin makes the cells inhospitable to the parasite. People with one sickle cell gene and one normal gene are protected from the worst effects of malaria while avoiding the serious problems of sickle cell disease. In regions where malaria is common, this balanced advantage has made the sickle cell gene surprisingly common, even though having two copies is harmful. This is a trade-off, a compromise that evolution has made. The sickle cell gene persists because the protection it provides against malaria outweighs the harm it causes in those unlucky enough to inherit two copies. The disease has shaped human genetics, maintaining a harmful gene in the population because, in the presence of malaria, that gene is also beneficial. Sickle cell is not the only genetic adaptation to malaria. There are others, many others. Thalassemia, another blood disorder, also provides some malaria resistance. Glucose 6-phosphate dehydrogenase deficiency, which affects how red blood cells handle oxidative stress, makes cells less hospitable to the malaria parasite. The Duffy-negative blood type, common in West Africa, provides near-complete immunity to one type of malaria by eliminating the receptor the parasite uses to enter red blood cells. Each of these adaptations comes with costs. Thalassemia can cause anemia and other health problems. G6PD deficiency can cause dangerous reactions to certain foods and medications. But in environments where malaria killed freely, these costs were worth paying. The populations that carry these genetic variants are the descendants of those who survived malaria, shaped by the disease into something different from populations that evolved without this selective pressure. The geographic distribution of these traits tells the story of malaria's influence. Sickle cell trait is common in Africa, the Middle East, and parts of India, all regions where malaria has been historically prevalent. Thalassemia is common around the Mediterranean and in Southeast Asia, again tracking with malaria distribution. The Duffy-negative blood type is found almost exclusively in people of African descent, reflecting the intense malaria pressure in sub-Saharan Africa. When scientists first discovered these genetic patterns, they were puzzled. Why would harmful genes be so common in certain populations? The answer, when it came, revealed something profound about how disease shapes human evolution. The genes were common not despite their harmful effects, but because of their beneficial effects in the presence of malaria. The disease had left its fingerprints on human DNA. Malaria shaped humanity in other ways beyond genetics. It influenced where humans could live and where they could not. Regions with intense malaria transmission were dangerous, and populations that moved into these regions faced heavy mortality until they developed resistance. This may have slowed human migration into certain areas, channeling the movement of peoples along routes where malaria was less severe. Malaria influenced human culture and behavior. Practices that reduced mosquito bites, from building houses with small windows to sleeping under nets, to draining standing water, were more likely to be adopted in malaria-endemic regions. The disease shaped architecture, agriculture, and daily routines, changing how people lived in subtle and not-so-subtle ways. Malaria influenced history. The disease protected Africa from European colonization for centuries. Europeans who ventured into tropical Africa died in such numbers that the continent was called the white man's grave. Only with the development of quinine, a malaria treatment derived from the bark of the cinchona tree, could Europeans survive long enough to establish colonies. The disease that had shaped African populations genetically also shaped African history by limiting outside intrusion. Tuberculosis, often called TB, is caused by bacteria, specifically Mycobacterium tuberculosis. Unlike malaria, which is transmitted by mosquitoes, tuberculosis spreads through the air from person to person, carried in tiny droplets expelled when an infected person coughs, sneezes, or even speaks. This mode of transmission makes tuberculosis a disease of proximity, a disease that thrives where humans live close together. Tuberculosis is old, perhaps as old as humanity itself. Evidence of TB has been found in the spines of ancient Egyptian mummies, in prehistoric bones from Europe and the Americas, in the remains of humans who lived thousands of years before the first written records. The disease has been with us for so long that it has become part of us, shaping our evolution in ways we are still discovering. The relationship between humans and tuberculosis is complex. The bacteria can infect anyone, but not everyone who is infected becomes sick. In most people, the immune system contains the bacteria, walling them off in structures called granulomas, where they can remain dormant for years or even decades. Only about 10% of people with latent TB infection ever develop active disease. The rest carry the bacteria without symptoms, a standoff between pathogen and immune system that can last a lifetime. This pattern of infection suggests a long co-evolution between humans and tuberculosis bacteria. A newly emerged pathogen is often highly virulent, killing its host quickly before the immune system can adapt. But tuberculosis has learned to coexist with us, to hide within our bodies without triggering a fatal response, to spread slowly and persistently rather than explosively. This is the mark of an old relationship, a disease and a host that have been shaping each other for millennia. The selective pressure from tuberculosis has left marks on the human genome, though these are less dramatic and less well understood than the marks left by malaria. Some studies have suggested that certain immune system genes are more common in populations with long histories of TB exposure, genes that might provide slight advantages in containing the infection. The evidence is still emerging, but the pattern is consistent with what we would expect from a disease that has been killing humans for thousands of generations. Tuberculosis shaped human history as well as human genetics. The disease thrived in cities where crowded conditions and poor ventilation allowed it to spread easily. As human civilization urbanized, tuberculosis followed, becoming the great killer of the industrial age. In 19th century Europe and America, TB was responsible for a quarter of all deaths. It was so common that it shaped culture, from the romantic ideal of the pale, consumptive poet to the architecture of sanatoria where patients sought fresh air and rest. The disease also shaped social structures. TB was associated with poverty, with crowded tenements, with the conditions of the working poor. Fear of the disease drove public health reforms, improved housing standards, and changed attitudes towards sanitation and ventilation. The battle against tuberculosis was one of the forces that created modern public health. The treatment of tuberculosis has evolved dramatically over the past century. Before antibiotics, patients were sent to sanatoria, where rest, fresh air, and good nutrition were the only treatments available. Many died anyway. The discovery of streptomycin in 1943 changed everything, providing the first effective treatment. Today, tuberculosis can be cured with a course of antibiotics lasting several months, though the emergence of drug-resistant strains threatens this progress. Despite these advances, tuberculosis remains a major killer. It causes more deaths than any other infectious disease, claiming over 1 million lives each year. The disease persists in populations with limited access to healthcare, in communities where poverty and crowding create ideal conditions for transmission. The battle against tuberculosis is not over. It continues, shaping humanity as it has for millennia. Plague is caused by Yersinia pestis, a bacterium that normally lives in rodents and their fleas. When conditions are right, when rodent populations explode, or when humans and rodents come into close contact, the bacteria can spill over into human populations, causing epidemics of devastating scope. There are 3 main forms of plague. Bubonic plague, the most common, infects the lymphatic system, causing the swollen lymph nodes called buboes that give the disease its name. Septicemic plague infects the bloodstream directly, causing rapid death. Pneumonic plague infects the lungs and can spread directly from person to person through respiratory droplets, making it the most dangerous form. Plague has caused some of the deadliest epidemics in human history. The plague of Justinian in the 6th century killed an estimated 25 to 50 million people, perhaps half the population of the Byzantine Empire. The Black Death in the 14th century killed an estimated 75 to 200 million people, wiping out a third to half of Europe's population. The third plague pandemic, beginning in the 19th century, killed millions more, primarily in Asia. These mass mortality events were catastrophic, traumatic on a scale almost impossible to imagine. In the years of the Black Death, entire villages were emptied, cities lost half their populations, bodies piled in streets faster than they could be buried. The social fabric tore apart as people fled from the sick, as families abandoned dying relatives, as the institutions that held society together collapsed under the weight of death. The Black Death arrived in Europe in 1347, carried by ships from the east. It spread with terrifying speed, moving along trade routes, following the paths of human connection. In some cities, the mortality rate exceeded 60%. Entire families died within days of each other. Priests who came to administer last rites often died themselves. Doctors, such as they were, could do nothing. The scale of death was so great that it transformed society. There were not enough living to bury the dead. Mass graves became common. The stench of decay hung over cities. Animals wandered untended through empty streets. The world as people knew it seemed to be ending. Recent studies of DNA from plague victims and their descendants have revealed that the Black Death was a selective event, favouring certain genetic variants over others. People with certain immune system genes were significantly more likely to survive the plague, and these genes became more common in the generations that followed. One particularly striking finding involves a gene called ERAP2. People with a certain variant of this gene were significantly more likely to survive the Black Death. This variant affects how the immune system presents pieces of the plague bacterium to the cells that fight infection. Having this variant meant a better immune response to plague and better odds of survival. But here is the twist. The same genetic variant that protected against plague appears to increase the risk of autoimmune diseases like Crohn's disease and rheumatoid arthritis. The survivors of the Black Death passed on genes that protected against plague, but that also made their descendants more vulnerable to autoimmune conditions. The disease shaped the population, but the shaping had consequences that extended far beyond the epidemic itself. Plague shaped history in ways that went beyond genetics. The massive population decline of the Black Death transformed European society. With fewer workers, labour became more valuable. Peasants could demand better conditions, and the rigid feudal system began to crack. Some historians argue that the Black Death was one of the factors that ended the Middle Ages and set the stage for the Renaissance and the modern world. The plague also shaped culture and psychology. The omnipresence of death during the Black Death led to new artistic and religious expressions, from the danse macabre motif showing death dancing with people of all social stations to the flagellant movements that swept Europe as people sought to appease God's wrath. The trauma of the plague was processed through culture, leaving marks that persisted for generations. Fear of plague shaped cities and governance. Quarantine, a word derived from the Italian 40 giorni meaning 40 days, was developed during plague outbreaks, with ships required to anchor offshore for 40 days before passengers could disembark. This was one of the first organised public health measures, an attempt to control disease spread that has shaped how societies respond to epidemics ever since. The plague never entirely went away. Smaller outbreaks continued for centuries after the Black Death. The Great Plague of London in 1665 killed perhaps a quarter of the city's population. Plague persists today in some parts of the world, though modern antibiotics have made it treatable if caught early. The disease that once killed millions now kills only hundreds each year, a testament to the power of medical progress. Smallpox was caused by the variola virus, a pathogen that infected only humans and had no animal reservoir. The disease spread through respiratory droplets and through contact with the distinctive pustules that covered infected patients. Once infected, a person would develop fever, then a rash that progressed to fluid-filled blisters, then to pustules, then to scabs that eventually fell off, leaving survivors scarred for life. The mortality rate varied but could reach 30% or higher in unvaccinated populations. Those who survived were immune for life, their bodies having learned to recognise and fight the virus. But survival often came at a terrible cost. Many survivors were left blind when the infection damaged their eyes. Many were disfigured, their faces permanently scarred by the pockmarks that gave the disease its name. Smallpox is ancient, with evidence suggesting it emerged thousands of years ago, possibly from a rodent virus that adapted to infect humans. Egyptian mummies from 3,000 years ago show the distinctive scarring of smallpox survivors. The disease spread wherever humans went, becoming endemic throughout Europe, Asia, and Africa. The virus was remarkably stable, not prone to the rapid mutation that characterizes some other viruses. This stability meant that immunity acquired from one infection protected against all strains, a characteristic that would eventually prove crucial to the disease's eradication. Smallpox shaped the fates of nations. The disease played a role in the decline of the Roman Empire, in the weakening of armies, in the outcomes of wars. European royalty were not immune. The disease killed queens and emperors, Altered lines of succession changed the course of history. But smallpox had never reached the Americas. When Europeans arrived in the New World, they brought smallpox with them, and the results were catastrophic. The indigenous peoples of the Americas had no inherited immunity, no genetic adaptations from generations of exposure, no experience with this particular viral enemy. Smallpox swept through Native American populations like fire through dry grass. The mortality rates were staggering. In some communities, 90% of the population died. Entire civilizations collapsed. The Aztec Empire, which had resisted Spanish military forces, fell when smallpox killed vast numbers of warriors and civilians, including the emperor himself. The Inca Empire suffered similar devastation. Across North and South America, millions died. Possibly the greatest demographic catastrophe in human history, this was disease as a weapon of conquest, though not intentionally at first. The Spanish did not need to understand germ theory to benefit from the epidemics that preceded and accompanied their invasions. The diseases did the work of armies, killing far more indigenous people than Spanish swords ever could. The populations that survived this Holocaust were changed. Those who lived through smallpox and the other diseases that Europeans brought were often those with some degree of genetic resistance or immune capability. The survivors repopulated the Americas, passing on whatever genetic advantages had helped them survive. The indigenous peoples of today are the descendants of those survivors, shaped by the diseases that killed their ancestors. Smallpox also shaped the populations of Europe, Asia, and Africa, but over a much longer time scale. These populations had been exposed to smallpox for thousands of years, and the genetic adaptations had accumulated gradually. The difference in mortality between Old World and New World populations during the Columbian Exchange reflected this difference in evolutionary history. The defeat of smallpox came through vaccination, a technique that itself arose from observation of the disease. Milkmaids who caught cowpox, a mild disease of cattle, rarely got smallpox. This observation led Edward Jenner to experiment with deliberate cowpox infection as protection against smallpox, creating the first true vaccine in 1796. Jenner's discovery was revolutionary. For the first time, humans had a tool to prevent a deadly disease before infection occurred. The word vaccine itself comes from vacca, the Latin word for cow, honouring the bovine origins of the technique. Over the following 2 centuries, vaccination campaigns gradually pushed smallpox back. The disease was eliminated from country after country, continent after continent. The effort required global cooperation, international coordination, and the dedication of thousands of health workers who travelled to the most remote villages to ensure that every person was vaccinated. In 1980, the World Health Organization declared smallpox eradicated. It was the first and so far only human disease to be completely eliminated through deliberate effort. The last natural case occurred in 1977 in Somalia. The virus now exists only in 2 laboratory freezers, one in the United States and one in Russia, preserved for research purposes. The eradication of smallpox stands as one of humanity's greatest achievements. It demonstrated that diseases can be defeated, that the selective pressures that had shaped humanity for millennia could be removed entirely. But the legacy of smallpox remains, written in the genes of populations around the world, in the history books that record its devastation, in the very concept of vaccination that arose from the fight against it. Cholera is caused by Vibrio cholerae, a bacterium that lives in water and infects the human digestive system. The disease causes profuse watery diarrhea that can lead to fatal dehydration within hours. A healthy person in the morning can be dead by evening if the disease goes untreated. The speed and violence of cholera made it one of the most feared diseases of the 19th century. Cholera was endemic in the Ganges Delta of India for centuries, but it burst onto the world stage in the early 19th century, spreading along trade routes to reach every inhabited continent. Between 1817 and 1923, there were 6 major cholera pandemics, killing millions of people worldwide. The disease thrived in the crowded, unsanitary cities of the industrial age. Human waste contaminated water supplies, and people drinking the contaminated water became infected, their waste further contaminating the water in a deadly cycle. Cholera was a disease of urbanization, of the failure of infrastructure to keep pace with population growth. The symptoms of cholera are horrific. The diarrhea is so profuse that patients can lose litres of fluid in hours. The body becomes desperately dehydrated. The skin loses its elasticity. The eyes sink into the skull. Without treatment, the heart eventually fails as the blood becomes too thick to pump. Death can come within 12 hours of the first symptoms. The response to cholera helped create modern epidemiology and public health. In London in 1854, a physician named John Snow traced a cholera outbreak to a single water pump on Broad Street. By mapping the cases and identifying the common source of infection, Snow demonstrated that cholera was spread through contaminated water, not through bad air as many believed. This was a foundational moment in epidemiology, the science of understanding how diseases spread through populations. Snow's methods were remarkably modern. He interviewed residents, mapped cases, calculated rates of infection in different areas. He noticed that people who drank from one water company had much higher cholera rates than those who drank from another. He traced the contamination to its source and convinced authorities to remove the handle from the Broad Street pump, ending the outbreak. Snow's work led to improvements in water supply and sanitation that eventually brought cholera under control in the developed world. The building of sewer systems, the treatment of drinking water, the separation of waste from water supply, all of these public health measures were driven in part by the fear of cholera. The disease shaped cities, transforming urban infrastructure in ways that benefited health far beyond cholera prevention. Cholera also left genetic marks on human populations, though these are less well studied than the marks left by malaria or plague. Some research suggests that people with certain blood types may be more susceptible to cholera, and that populations with long histories of cholera exposure may have shifted blood type frequencies as a result. The cystic fibrosis gene, which causes a serious lung disease in those who inherit 2 copies, may persist partly because carriers have some resistance to cholera. Like sickle cell and malaria, this would be another example of a disease maintaining a harmful gene by providing a counterbalancing benefit. The evidence is not conclusive, but the pattern suggests that cholera, like other major diseases, has left its mark on human genetics. Cholera remains a threat in parts of the world where clean water and sanitation are not available. Outbreaks continue to occur, particularly in areas affected by war, natural disaster, or extreme poverty. The disease that helped create modern public health continues to reveal where public health has failed. Influenza is caused by viruses that infect the respiratory system. The disease ranges from mild to severe, and while most people recover within a week or 2, some develop complications that can be fatal. What makes influenza particularly dangerous is its ability to change, to mutate and recombine, creating new strains against which existing immunity is useless. The influenza virus has 2 key proteins on its surface, hemagglutinin and neuraminidase, abbreviated as H and N. Different strains are named for their particular versions of these proteins, H1N1, H3N2, and so on. The virus can change these proteins through mutation, gradually drifting away from forms that the immune system recognizes. It can also change suddenly through reassortment, when 2 different strains infect the same cell and swap genetic material, potentially creating entirely new combinations. This changeability means that influenza is always with us. Unlike smallpox, which could be eradicated because it did not change and had no animal reservoir, influenza constantly evolves and maintains reservoirs in birds and pigs. We cannot eliminate influenza, we can only try to keep up with it, developing new vaccines each year to match the currently circulating strains. Influenza has caused many pandemics throughout history, but the deadliest was the 1918 flu, sometimes called the Spanish flu. This pandemic infected an estimated 500 million people, about a third of the world's population at the time, and killed an estimated 50 to 100 million people. The death toll was greater than that of World War I, which was happening simultaneously. The 1918 flu was unusual in several ways. Most flu strains kill primarily the very young and the very old, those with the weakest immune systems. But the 1918 flu killed young, healthy adults in disproportionate numbers. It may have triggered an excessive immune response called a cytokine storm, where the immune system's reaction to the virus caused more damage than the virus itself. The stronger the immune system, the more dangerous this overreaction could be. The virus spread with terrifying speed. In some cities it seemed to appear everywhere at once. Hospitals were overwhelmed. Morgues ran out of coffins. In some places there were not enough healthy people to care for the sick or bury the dead. The social disruption was immense, compounded by the ongoing war. The crowded conditions of wartime accelerated the spread. Soldiers packed into barracks and transport ships provided ideal conditions for transmission. The movement of troops across continents carried the virus around the world. Some historians have suggested that the flu may have influenced the outcome of the war, weakening armies and affecting the ability of nations to fight. The 1918 flu shaped the 20th century. It killed more people than the war that accompanied it, influencing the peace negotiations and the post-war world. It demonstrated the vulnerability of modern connected societies to pandemic disease. It influenced public health policy and medical research for decades, and it left genetic marks on the survivors and their descendants. Influenza continues to pose a threat. New strains emerge regularly from the animal reservoirs where the virus circulates. The 2009 H1N1 pandemic was a reminder that pandemic influenza can appear at any time. The fear of a 1918-scale pandemic drives ongoing surveillance of flu viruses worldwide, monitoring for the emergence of new strains that could spread rapidly and kill millions. The annual flu vaccine is a testament to our ongoing battle with this shape-shifting virus. Each year, scientists predict which strains will circulate and formulate a vaccine to match. Sometimes they predict well, sometimes they miss. The imperfection of flu vaccines reflects the difficulty of hitting a moving target, of defending against an enemy that is always changing. For most of human existence, our ancestors lived as hunter-gatherers, moving in small groups across the landscape, following game and gathering plants. This lifestyle had a particular disease profile. Hunter-gatherers were exposed to parasites they picked up from the environment, to infections they caught from the animals they hunted, to the diseases that spread within their small groups. But they were largely protected from the epidemic diseases that would later devastate humanity. This is because epidemic diseases need large, dense populations to sustain themselves. A disease that spreads quickly and either kills or immunizes its victims will burn through a small group and then disappear, unable to find new susceptible hosts. The epidemic diseases that we have discussed, smallpox and measles, plague and cholera, need cities, need thousands or millions of people living close together to maintain continuous transmission. The agricultural revolution, which began about 10,000 years ago, changed everything. When humans began to farm, they settled down. They built permanent villages that grew into towns and eventually cities. Populations increased as agriculture produced more food per acre than hunting and gathering. People lived closer together, in densities that had never existed before. These conditions were ideal for epidemic diseases. Dense populations provided large numbers of susceptible hosts. Permanent settlements accumulated waste and contaminated water supplies. The proximity of humans and their domestic animals created opportunities for diseases to jump from animals to humans. Agriculture created the conditions for the diseases that would shape human history. The domestication of animals was particularly important. Many of the most devastating human diseases originated in animals and adapted to infect humans. Measles likely came from a virus of cattle. Smallpox may have come from a rodent or a cow. Influenza circulates among birds and pigs before spilling over into humans. Tuberculosis may have been transmitted to humans from cattle. By living close to animals, feeding them, breathing their air, drinking their milk, humans exposed themselves to pathogens that would never have reached them in their hunter-gatherer past. This process, called zoonosis, continues today. HIV jumped from chimpanzees to humans through contact with infected blood during hunting. SARS and COVID-19 originated in bats and may have passed through intermediate animal hosts before reaching humans. Ebola, Nipah, and many other emerging diseases have animal origins. Our relationship with animals, both domestic and wild, continues to expose us to new pathogens with the potential to cause epidemics. The early agricultural societies paid a heavy price for their new way of life. Skeletal remains show that early farmers were shorter than their hunter-gatherer ancestors, a sign of nutritional stress and chronic disease. They had more dental cavities, from diets heavy in carbohydrates. They had more signs of infection, more evidence of disease. The agricultural revolution was not immediately healthy for the individuals who lived through it. But agriculture persisted because it allowed populations to grow. Even though individuals were less healthy, there were more of them. The agricultural societies outcompeted the hunter-gatherers, expanding their territories, absorbing or displacing the smaller groups that had not adopted farming. The diseases of civilization were terrible, but they were part of a package that ultimately proved successful in evolutionary terms. Over millennia, agricultural populations adapted to their new disease environment. The selective pressure from epidemic diseases shaped their genomes, favouring individuals with resistance or tolerance to the diseases they faced. The populations that survived the diseases of civilization were changed by them, carrying genetic adaptations that their hunter-gatherer ancestors had not needed. When these adapted populations encountered populations that had not been through this selective filter, the results were devastating. The European conquest of the Americas was not just a military conquest, it was a biological one. The diseases that Europeans carried, to which they had partial resistance from generations of exposure, devastated indigenous populations that had no such resistance. The same pattern repeated in Australia, in the Pacific Islands, wherever populations with different disease histories came into contact. Before vaccines, virtually every child caught measles, mumps, rubella, chickenpox, and a host of other infections. These childhood diseases were so common that they were considered normal, a rite of passage that everyone went through. Families would even deliberately expose children to infections, preferring that they catch them while young when the diseases were typically milder. Measles is one of the most contagious diseases known, spreading through respiratory droplets with extraordinary efficiency. Before vaccination, virtually every child caught measles, and the disease killed millions each year. Measles evolved from a virus of cattle, rinderpest, making the jump to humans sometime in the past 2,000 years. The virus adapted to human transmission, eventually losing its ability to infect cattle while becoming perfectly adapted to infect humans. Measles shaped human populations by killing the susceptible and sparing the resistant. In populations with long measles exposure, the disease is primarily one of childhood, and most people survive with lifelong immunity. But in populations encountering measles for the first time, the disease can be catastrophic. The virgin soil epidemics that struck the Americas and the Pacific killed adults as well as children, sometimes eliminating a quarter or more of the population. These childhood diseases were not harmless. Measles killed thousands of children each year, and those who survived sometimes suffered brain damage or other complications. Mumps could cause deafness. Rubella in pregnant women could devastate developing fetuses. Chickenpox, usually mild, could be severe or fatal in some cases. The acceptance of these diseases as normal reflected their inevitability, not their safety. Pertussis, or whooping cough, is another disease that shaped childhood mortality for centuries. The distinctive whoop of a child trying to catch breath between coughing fits was a familiar and feared sound before vaccination made the disease rare. Pertussis killed primarily infants, too young to have developed immunity, too weak to survive the violent coughing that characterized the disease. Diphtheria was another childhood killer, causing a thick membrane to form in the throat that could block the airway and suffocate the victim. Before antitoxin treatment and vaccination, diphtheria epidemics swept through cities, killing thousands of children. The disease was so feared that the race to deliver diphtheria antitoxin to Nome, Alaska, during a 1925 epidemic became legendary, commemorated in the annual Iditarod sled dog race. Vaccination changed this. Children today can be protected from diseases that their grandparents caught as a matter of course. The childhood that was once shaped by inevitable infection is now shaped by scheduled vaccinations, by immune protection without the risks of natural infection. The diseases that shape childhood have been largely removed from childhood, at least in populations with access to vaccines. This is a change in how disease shapes humanity. Natural infection selected for genetic resistance. Vaccination protects regardless of genetics. Natural infection killed and disabled. Vaccination prevents without harm. The selective pressure of childhood disease has been reduced, replaced by a protective technology that circumvents natural selection entirely. Syphilis is caused by the bacterium Treponema pallidum, which spreads through sexual contact and from mother to child. The disease progresses through stages, from initial sores to rash to, in some cases, devastating late-stage effects on the heart, brain, and other organs. Untreated syphilis can be fatal, and even non-fatal cases can cause serious disability. The origin of syphilis is debated. One theory holds that it was brought to Europe from the Americas by Columbus's crew, while another suggests it existed in Europe before Columbus, but was not recognized as a distinct disease. Whatever its origin, syphilis became a major epidemic in Europe in the late 15th and early 16th centuries, killing thousands and terrifying populations who did not understand how it spread. syphilis shaped sexual behavior by providing a powerful incentive for monogamy and caution. The disease was associated with prostitution and promiscuity, adding moral weight to sexual restraint. The fear of syphilis influenced marriage customs, sexual norms, and cultural attitudes towards sexuality. The disease was a selective pressure on behavior as well as genetics. The development of effective treatment for syphilis, first with arsenic compounds and then with penicillin, transformed the disease from a terrifying killer to a treatable infection. But syphilis has not been eliminated. It persists, especially in populations without access to diagnosis and treatment. And the behavioral changes that fear of syphilis once motivated have relaxed, contributing to the spread of this and other sexually transmitted diseases. Gonorrhea is another ancient sexually transmitted disease caused by the bacterium Neisseria gonorrhoeae. The disease causes painful urination and discharge, and in women can lead to pelvic inflammatory disease and infertility. Gonorrhea has been shaping human populations for thousands of years, selecting for immune responses that can control the infection, and for behaviors that avoid transmission. HIV, the human immunodeficiency virus, emerged in the 20th century from a virus of chimpanzees. HIV attacks the immune system itself, destroying the CD4 T cells that coordinate the immune response. Without treatment, HIV infection progresses to AIDS, acquired immunodeficiency syndrome, leaving the patient vulnerable to opportunistic infections and cancers that a healthy immune system would control. The HIV/AIDS epidemic has killed an estimated 35 million people since it began, making it one of the deadliest epidemics in human history. The disease has shaped populations in sub-Saharan Africa, where HIV prevalence is highest, selecting for genetic variants that provide some resistance to infection or that slow disease progression. The CCR5 delta 32 mutation, which provides near-complete immunity to certain strains of HIV, has been intensely studied as scientists seek to understand why some people resist infection. HIV has shaped human behavior on a global scale. Fear of AIDS drove changes in sexual practices, promoted condom use, and altered attitudes toward homosexuality and drug use. The epidemic created new institutions, new research priorities, new social movements. The disease has touched virtually every aspect of human society, from personal relationships to international politics. The development of antiretroviral therapy has transformed HIV from a death sentence to a chronic condition. People with HIV who take their medications can expect near-normal lifespans. They can have children without transmitting the virus. They can live full lives, the disease managed if not eliminated. This transformation required decades of research, billions of dollars, and the activism of affected communities who demanded that their lives be treated as worth saving. Emerging diseases are infections that have recently appeared in human populations or that have existed but are rapidly increasing in incidence or geographic range. They arise from the same processes that have always generated new diseases: animal viruses adapting to infect humans, existing pathogens evolving new capabilities, human activities creating new opportunities for transmission. HIV was an emerging disease in the 1980s, a new infection that spread rapidly and killed millions before treatments were developed. Ebola emerged in 1976, causing small but terrifying outbreaks in Central Africa, before exploding into the 2014 to 2016 West African epidemic that killed over 11,000 people. SARS appeared in 2003, spreading from China to cause outbreaks worldwide before being contained. MERS emerged in 2012, a coronavirus from camels that continues to cause sporadic cases in the Middle East. COVID-19 is the most recent example of an emerging disease, a coronavirus that appeared in late 2019 and rapidly spread to become a global pandemic. The disease has killed millions, disrupted economies, and transformed daily life for billions of people. It is a reminder that despite all our medical advances, we remain vulnerable to new pathogens, that the evolutionary creativity of the microbial world continues to generate threats faster than we can prepare for them. The factors that promote disease emergence are intensifying. Human populations are growing and spreading into previously wild areas, increasing contact with animal reservoirs. Climate change is altering the distribution of disease vectors, allowing tropical diseases to spread to new regions. Global travel and trade connect populations as never before, allowing a disease that emerges anywhere to spread everywhere within weeks. The COVID-19 pandemic revealed both the power of modern medicine and its limitations. Vaccines were developed with unprecedented speed, but their distribution was uneven. Public health measures worked, but they were politically contested. The pandemic was eventually controlled, but not before millions died. The response showed what humanity can do when mobilized, but also how far we have yet to go. Future pandemics are inevitable. The question is not whether they will occur, but how severe they will be and how well we will respond. Preparation now, investment in surveillance and research and public health infrastructure can reduce the toll of future outbreaks. Neglect now will be paid for in lives later. Your immune system is a marvel of biological engineering, the product of hundreds of millions of years of evolution. It has two main branches: the innate immune system, which provides rapid, non-specific defense against invaders, and the adaptive immune system, which provides slower but highly specific responses that can remember past threats and respond more effectively to them in the future. The innate immune system is ancient, shared with virtually all animals. It includes physical barriers like skin and mucous membranes, chemical defenses like the acid in your stomach, and cellular responders like macrophages that engulf and destroy invaders. These defenses are always ready, always on guard, the first line of defense against any pathogen. The adaptive immune system is more recent, appearing in vertebrates about 500 million years ago. It is built around two types of cells: B cells, which produce antibodies, and T cells, which coordinate the immune response and directly kill infected cells. The key feature of the adaptive system is its ability to generate an enormous diversity of receptors, each capable of recognizing a specific pathogen, and to remember which pathogens it has encountered before. This memory is the basis of immunity. When you survive an infection or receive a vaccine, your adaptive immune system remembers the pathogen. If you encounter it again, your immune response is faster and stronger, often eliminating the threat before you even develop symptoms. This is why you can only get measles once, why vaccination works, why surviving certain diseases protects you for life. The evolution of the adaptive immune system was driven by the arms race between hosts and pathogens. As pathogens evolved new ways to infect and evade defenses, hosts evolved new ways to recognize and eliminate them. The diversity of the adaptive immune system, its ability to recognize virtually any pathogen, is the result of this ongoing evolutionary competition. But the pathogens have not been passive. They have evolved their own countermeasures, ways to hide from the immune system, to suppress it, to turn it against the host. The influenza virus changes its surface proteins to evade recognition. HIV attacks the very immune cells that should eliminate it. Tuberculosis bacteria hide inside the immune cells sent to destroy them. The war continues, with each side evolving new weapons and defenses. The diseases that have shaped humanity have also shaped our immune systems. Populations exposed to malaria have evolved not just blood cell changes, but also immune system differences that affect how they respond to the parasite. Populations with long histories of tuberculosis exposure may have enhanced immune responses to the bacteria. The selective pressure of disease has tuned human immune systems differently in different populations, creating diversity that reflects the different disease environments our ancestors faced. You're not just human, you're a walking ecosystem, home to trillions of bacteria, viruses, fungi, and other microorganisms. These microbes live on your skin, in your mouth, in your gut, in virtually every part of your body that is exposed to the outside world. They outnumber your human cells, though they are much smaller. They carry more genes than your human genome. They are, in a very real sense, part of you. The relationship between humans and our microbiome is ancient, stretching back to the first animals and probably before. We have co-evolved with our microbial passengers, each shaping the other over millions of years. Many of our microbes are beneficial, helping us digest food, producing vitamins, training our immune systems, protecting us from harmful pathogens. We could not live without them, but the microbiome is also shaped by disease. When a pathogen invades, it disrupts the microbial community. The immune response that fights the pathogen also affects the resident microbes. Antibiotics that kill harmful bacteria also kill beneficial ones. The aftermath of infection is a changed microbiome, a new balance of microbial species that may persist long after the pathogen is gone. The diseases that have shaped humanity have also shaped our microbiomes. Populations that have faced particular diseases have microbiomes adapted to those disease pressures. The selective forces that have shaped human genetics have also shaped the genetics of our microbial partners. We are not just survivors of disease, we are ecosystems shaped by disease. The modern world has changed our microbiomes in ways we're only beginning to understand. Antibiotics have saved millions of lives, but they have also disrupted microbial communities. Sanitation has eliminated many diseases, but it has also reduced our exposure to microbes that might benefit us. Modern diets, processed and low in fiber, do not feed our gut bacteria the way traditional diets did. Some researchers believe that these changes to our microbiomes are contributing to the rise of autoimmune diseases, allergies, and other conditions that were rare in traditional societies. The hygiene hypothesis suggests that our immune systems evolved to cope with constant microbial challenge, malfunction when that challenge is removed. We may be too clean for our own good, missing the microbial exposures that shaped our immune development. This is another way that disease shapes humanity, not just through the infections that kill us, but through the infections that train us, that educate our immune systems, that maintain the microbial ecosystems that we depend upon. Our relationship with the microbial world is complex, and disrupting it has consequences we are still discovering. Heart disease, cancer, diabetes, obesity, these are the leading causes of death in the developed world. They are not infectious diseases. They are chronic conditions that develop over years and decades, influenced by genetics, behavior, and environment. But they are also selective forces, shaping human populations just as infectious diseases have. Heart disease kills millions each year, more than any infectious disease. It is influenced by genes that affect cholesterol metabolism, blood pressure, and inflammation. These genes were not always harmful. In ancestral environments, they may have been beneficial, helping to store energy during famines or to heal wounds quickly. But in modern environments, with abundant food and little exercise, these same genes contribute to clogged arteries and heart attacks. The genes that predispose to heart disease are still being selected against. People who die young from heart attacks leave fewer descendants than those who live longer. But the selection is slow, and the genes are maintained by their benefits in other contexts. Heart disease is shaping human populations, but the shaping happens over generations, too slow for any individual to notice. Cancer is another major selective force. The genes that control cell division, that repair DNA damage, that suppress tumor growth, are under constant selective pressure. Mutations that increase cancer risk are selected against when they kill before reproduction. But many cancers occur later in life, after reproduction is complete, and so the genes that contribute to them are not strongly selected against. The relationship between cancer and evolution is complex. Some cancer-protective genes may have other costs, reducing fertility or growth. Some cancer-promoting genes may have benefits, increasing reproductive success early in life, even at the cost of cancer later. The human genome reflects these trade-offs, carrying genes that balance the benefits of growth and reproduction against the risks of uncontrolled cell division. Diabetes, particularly type 2 diabetes, has become epidemic in modern populations. The disease is influenced by genes that affect insulin sensitivity and glucose metabolism, genes that may have been beneficial when food was scarce and uncertain. In environments of abundance, these thrifty genes contribute to obesity and diabetes, conditions that would have been rare in ancestral populations. The rise of diabetes is a reminder that genetic adaptations are not always beneficial. Genes that evolved in one environment may be harmful in another. The diseases of civilization are, in part, the result of a mismatch between our evolved genetics and our current environment. Antibiotics are one of the greatest medical achievements of the 20th century. Infections that were once death sentences became treatable. Surgeries that would have been too dangerous became routine. Millions of lives have been saved by these drugs that kill bacteria, but bacteria evolve. Those that survive antibiotic treatment are, by definition, resistant. They reproduce, passing on their resistant genes. Over time, resistant strains become more common, until the antibiotic loses its effectiveness. This process, called antibiotic resistance, is now threatening to undo the medical progress of the past century. Antibiotic resistance is an example of evolution in action, of natural selection happening on a timescale we can observe. The selective pressure is the antibiotic itself. The survivors are those bacteria with resistance. The result is a population of bacteria that cannot be killed by drugs that once eliminated them easily. Some bacteria are now resistant to almost all available antibiotics. Infections caused by these superbugs are difficult or impossible to treat, killing patients who would have survived a few decades ago. The pipeline of new antibiotics has slowed, as drug companies have found it more profitable to develop drugs for chronic conditions than for acute infections. We are approaching a post-antibiotic era, where infections once again become untreatable. This is disease shaping humanity in a new way. For most of history, disease has shaped us through natural selection, killing those without resistance. Now disease is being shaped by us, evolving in response to our interventions. The relationship between humans and pathogens is entering a new phase, one where our actions drive microbial evolution in unpredictable and dangerous directions. The response to antibiotic resistance requires evolution on our side. We need new antibiotics, new approaches to treating infection, new ways to stay ahead of bacterial evolution. We need to use existing antibiotics more wisely, reducing the selective pressure that drives resistance. We need to understand that the war between humans and microbes is not won but ongoing, and that our weapons will become useless unless we use them carefully. The human leukocyte antigen system, or HLA, is a set of genes that plays a central role in the immune response. These genes code for proteins that display pieces of pathogens on cell surfaces, allowing the immune system to recognize and respond to infections. The HLA genes are the most diverse in the human genome, with thousands of variants that differ in the pathogens they recognize. This diversity is maintained by disease. Different HLA variants recognize different pathogens more effectively. In a population facing multiple diseases, the individuals with rare HLA variants may have advantages when those variants happen to recognize a current pathogen well. This frequency-dependent selection maintains diversity, preventing any single variant from becoming dominant. The distribution of HLA variants reflects the disease histories of human populations. Populations that have faced particular diseases often have higher frequencies of HLA variants that provide resistance to those diseases. The HLA diversity of a population is a record of its disease history, a genetic memory of the selective pressures its ancestors faced. Other immune genes show similar patterns. The toll-like receptors, which recognize pathogen components and trigger innate immune responses, vary between populations in ways that reflect disease exposure. The cytokine genes, which control immune signaling, show signatures of selection related to specific diseases. The human immune system is a palimpsest of evolutionary responses to past threats. Some disease resistance genes have become famous because they provide protection against HIV. The CCR5-delta32 mutation, which deletes part of a gene used by HIV to enter cells, provides near-complete immunity to certain HIV strains. This mutation is found in about 10% of Europeans but is rare or absent in African and Asian populations. The origin of CCR5-delta32 is debated. Some researchers suggested it was selected by plague, which may also use CCR5 for cell entry. Others have proposed smallpox as the selective agent. The mutation appears to have risen to its current frequency relatively recently, perhaps within the last few thousand years, suggesting strong positive selection by some disease. Whatever the cause, CCR5-delta32 is an example of how disease creates genetic differences between human populations. While the wealthy nations have largely controlled the diseases that once devastated their populations, much of the world still lives with infections that shape daily life and limit human potential. These are the diseases of poverty, persistent, because the conditions that allow them to thrive, inadequate sanitation, unsafe water, crowded housing, limited healthcare, persist as well. Malaria remains one of the leading causes of death in sub-Saharan Africa. Despite decades of effort, despite insecticide-treated bed nets and anti-malarial drugs, the disease continues to kill hundreds of thousands of children each year. A child dies of malaria approximately every minute. The burden of malaria has shaped not just genetics but economic development, as the disease saps productivity, keeps children out of school, and diverts resources from other needs. The economic impact of malaria is staggering. Countries with high malaria burdens have lower economic growth, not just because of the direct costs of treatment and prevention, but because of the indirect costs of lost productivity, reduced investment, and impaired education. Malaria perpetuates poverty, and poverty perpetuates malaria, a cycle that is difficult to break. Schistosomiasis is a parasitic disease caused by flatworms that live in freshwater snails and infect humans who wade or swim in infested water. The parasites burrow through the skin, migrate to the blood vessels around the intestines or bladder, and produce eggs that cause inflammation and scarring. Chronic schistosomiasis can lead to liver damage, bladder cancer, and other serious complications. Hundreds of millions of people are infected, mostly in Africa and Asia. The life cycle of the schistosome parasite is remarkable in its complexity. The eggs, passed in human waste, hatch in fresh water and infect snails. Inside the snails, the parasites multiply and release free-swimming forms that can penetrate human skin. A brief wade through infested water can result in an infection that lasts for years. The disease persists because people must use the water for drinking, for washing, for farming, and because the sanitation infrastructure that would break the cycle does not exist. Hookworm, roundworm, and other soil-transmitted helminths infect billions of people worldwide, causing malnutrition, anemia, and developmental problems, especially in children. These parasites spread through fecal contamination of soil, infecting people who walk barefoot or eat contaminated food. They are diseases of poverty, persisting where sanitation is inadequate and where people cannot afford shoes or clean water. The impact of these worm infections on children is profound. Heavy parasite burdens impair growth, reduce cognitive development, and decrease school performance. Children with chronic infections grow up to be less productive adults, perpetuating the cycle of poverty. The treatment is simple and cheap. A few pills can eliminate the worms, but reaching everyone who needs treatment and preventing reinfection requires infrastructure and resources that many communities lack. Trachoma, caused by the bacterium Chlamydia trachomatis, is the leading infectious cause of blindness worldwide. The infection spreads through contact with eye discharge, often carried by flies that breed in human waste. Repeated infections cause scarring of the inner eyelid, which eventually turns inward and scratches the cornea with every blink. The result is painful, progressive blindness. Millions of people, mostly in the poorest regions of Africa and Asia, are at risk. The tragedy of trachoma is that it is entirely preventable. Face washing, improved sanitation, and access to antibiotics can eliminate the disease. Where these interventions have been implemented, trachoma has disappeared. But in communities without clean water, without latrines, without healthcare, the disease persists, blinding generation after generation. River blindness, caused by a parasitic worm transmitted by black flies that breed near fast-flowing rivers, has devastated communities throughout Africa and parts of the Americas. The adult worms live under the skin, producing millions of microscopic larvae that migrate through the body, including to the eyes. When the larvae die, they trigger an inflammatory response that can cause blindness. Entire villages near rivers have been abandoned because so many residents went blind. The control of river blindness is one of the great success stories of global health. The drug ivermectin, donated by its manufacturer, kills the larvae and prevents blindness if taken annually. Mass drug administration programs have dramatically reduced the disease burden, and elimination is now within reach in some areas. But the programs must continue for decades, until the adult worms die of old age, and maintaining that commitment requires sustained resources and political will. These diseases of poverty shape populations in ways that are harder to see, but no less real than the effects of acute epidemics. Chronic infection drains energy, impairs growth, reduces productivity. The diseases perpetuate poverty, creating a cycle that is difficult to break. The distribution of these diseases is not accidental. They persist in the tropics because the climate favors the parasites and their vectors. They persist among the poor because the poor lack access to clean water, sanitation, shoes, medication. The diseases of poverty are both biological phenomena and social ones, shaped by human choices about resource distribution and priorities. Many people carry pathogens that cause no symptoms. These silent infections persist in the body, held in check by the immune system but never eliminated, ready to cause disease if circumstances change. Tuberculosis bacteria can lie dormant in the lungs for decades, walled off by the immune system in structures called granulomas. Most people with latent TB never develop active disease, but if the immune system weakens, through age, through HIV infection, through immunosuppressive drugs, the bacteria can reactivate, multiplying and causing disease years or decades after the initial infection. An estimated quarter of the world's population carries latent TB. Herpes viruses, once contracted, persist for life in nerve cells. The virus that causes cold sores hides in the nerves of the face, emerging periodically to cause the familiar blisters. The virus that causes chickenpox retreats to spinal nerve cells, where it can remain dormant for decades before reactivating as shingles, a painful rash that follows the path of the infected nerve. Most adults carry multiple herpes viruses, permanent passengers acquired in childhood. Hepatitis B and C can smoulder in the liver for years, causing gradual damage that only becomes apparent when the organ begins to fail. People with chronic hepatitis often feel fine for decades, unaware that the virus is slowly destroying their liver. By the time symptoms appear, the damage may be irreversible. Chronic hepatitis is a leading cause of liver cancer and cirrhosis worldwide. Epstein-Barr virus, the cause of mononucleosis, infects most people during childhood, usually without symptoms. The virus then persists in B cells, the immune cells that produce antibodies, remaining dormant but occasionally reactivating. Most of the time, the immune system keeps the virus in check, but Epstein-Barr virus is associated with several cancers and may play a role in autoimmune diseases like multiple sclerosis. Cytomegalovirus infects most adults, usually without causing any symptoms. The virus persists in various cells throughout the body, reactivating occasionally, but rarely causing problems in healthy people. However, in people with weakened immune systems, transplant recipients, AIDS patients, newborns, cytomegalovirus can cause serious disease, including blindness, pneumonia, and brain damage. Helicobacter pylori, the bacterium that causes stomach ulcers, infects about half the world's population. Most people with H. pylori never develop ulcers or other problems. The bacterium lives in the mucus layer of the stomach, evading the immune system and the harsh acid environment. For reasons that are not fully understood, some people develop ulcers or stomach cancer, while others remain healthy carriers for life. These silent infections remind us that the relationship between humans and pathogens is not always straightforward. Not every infection causes disease. Many pathogens have evolved to coexist with their hosts, causing minimal harm while ensuring their own survival and transmission. The line between pathogen and passenger is blurrier than it might seem. You may carry silent infections right now. Most adults carry herpes viruses, acquired in childhood and persistent ever since. Many carry Epstein-Barr virus, cytomegalovirus, or other pathogens, unknown passengers on the journey of life. These infections are part of what disease has made us. They are not separate from us, but part of us, incorporated into our bodies, influencing our immune systems, contributing to the complex ecosystem that is a human being. When you emerged from your mother's womb, you entered a world teeming with microbes. The sterile environment of the uterus gave way to air filled with bacteria, to surfaces covered with fungi, to hands that touched you bringing their microbial passengers. In those first moments of life, your immune system faced its initial test. You were not undefended. Your mother had given you antibodies, passed through the placenta in the final months of pregnancy. These maternal antibodies protected you for your first months of life, bridging the gap until your own immune system could mature. You also received antibodies through breast milk, concentrated in the colostrum that was your first food. These borrowed defenses kept you alive while your own defenses developed. The microbes that colonized you in those first days and weeks were not random. The bacteria you encountered during birth, whether through the birth canal or during skin-to-skin contact, began to establish your microbiome. The first colonizers shaped the community that would develop, influencing which species could establish themselves later. Your microbiome began to form at the moment of birth, shaped by the microbes in your immediate environment. Babies born by caesarean section have different microbiomes than those born vaginally, at least in the first months of life. They're colonized first by skin bacteria rather than vaginal bacteria, which may have health implications that researchers are still investigating. Some studies suggest higher rates of allergies and autoimmune diseases in caesarean-born children, though the evidence is not conclusive. This colonization was essential. Without microbes, your immune system would not develop properly. The bacteria that colonized your gut trained your immune cells, teaching them what was normal, what should be tolerated, what should be attacked. This education was crucial. Without it, your immune system might attack your own tissues or respond inappropriately to harmless substances. The diseases that shaped humanity shaped this process too. Infants have evolved to be colonized, to receive microbial education, to develop immune systems through interaction with the microbial world. The precise balance of challenge and tolerance, of defense and acceptance, was refined over millions of generations of infants who survived or did not survive the gauntlet of early life. The vulnerability of infants to disease has shaped human culture as well as biology. In many traditional societies, newborns were kept isolated, protected from visitors who might bring infection. Naming ceremonies were delayed until the child had survived the dangerous early weeks. These practices, whatever their ritual significance, reflected the reality that many infants did not survive, and that protecting them from disease was crucial. Modern medicine has transformed infant survival. Vaccines protect against diseases that once killed thousands of babies each year. Antibiotics can cure infections that would have been fatal. Clean water and sanitation prevent the diarrheal diseases that were once the leading cause of infant death. In wealthy countries, infant mortality has fallen to historically unprecedented levels. But this transformation is not complete. Millions of infants still die each year from preventable causes, most of them in the poorest countries. Pneumonia, diarrhea, malaria, diseases that wealthy countries have largely controlled, continue to kill children whose only misfortune was to be born in the wrong place. The diseases that shaped humanity continue to shape it, selecting for survival in populations that cannot access the medical advances that protect others. Many of the diseases that have shaped humanity are not transmitted directly from person to person. Instead, they require vectors, organisms that carry the pathogen from one host to another. Understanding these vectors has been crucial to controlling the diseases they spread. Mosquitoes are the deadliest animals on Earth, not because of anything they do themselves, but because of the diseases they carry: malaria, dengue, yellow fever, Zika, chikungunya, West Nile virus. The list of mosquito-borne diseases is long and deadly. Mosquitoes have killed more humans than all wars combined, making them humanity's most lethal enemy. Different mosquito species transmit different diseases. Anopheles mosquitoes carry malaria. Aedes mosquitoes carry dengue, yellow fever, and Zika. Culex mosquitoes carry West Nile virus and some forms of encephalitis. Each species has different habits, different breeding sites, different geographic ranges, requiring different control strategies. The female mosquito needs blood to produce eggs, and it is this blood meal that transmits disease. When a mosquito feeds on an infected person, it ingests the pathogen along with the blood. The pathogen then multiplies within the mosquito and migrates to its salivary glands. When the mosquito feeds again, it injects saliva containing the pathogen into the next victim. The mosquito itself is usually unharmed. It is merely a vehicle for the pathogen's transmission. Control of mosquito-borne diseases has relied on various strategies. Draining standing water eliminates breeding sites. Insecticides kill adult mosquitoes and larvae. Bed nets prevent bites during the night when many mosquito species are most active. Window screens keep mosquitoes out of homes. Each strategy has its limitations, and the most effective control programs use multiple approaches simultaneously. Fleas were the vectors of plague, carrying Yersinia pestis from rats to humans. The flea feeds on an infected rat, ingesting the plague bacteria. The bacteria multiply in the flea's gut, eventually blocking it so that the flea cannot digest its blood meals. The starving flea bites more aggressively, regurgitating bacteria into each bite wound. When the rats die, the fleas seek new hosts, including humans. Understanding this transmission cycle was crucial to controlling plague. Rat control, improved sanitation, and public health measures that reduce contact between humans, rats, and fleas have largely eliminated plague from the developed world. But plague persists in wild rodent populations, and occasional cases still occur when humans come into contact with infected animals or their fleas. Ticks transmit Lyme disease, Rocky Mountain spotted fever, and numerous other infections. Unlike mosquitoes, which feed quickly and fly away, ticks attach and feed for days, increasing the opportunity for pathogen transmission. Ticks are expanding their range as climate change warms previously inhospitable regions, bringing tick-borne diseases to new areas. Tsetse flies transmit African sleeping sickness, a parasitic disease that is fatal if untreated. The flies are found only in sub-Saharan Africa, and their presence has shaped human settlement patterns for millennia. Regions with heavy tsetse fly populations were dangerous for humans and livestock alike, limiting agriculture and development. Control of tsetse flies has been a priority for African nations seeking to develop affected regions. Sandflies transmit leishmaniasis, a parasitic disease that can cause disfiguring skin lesions or fatal internal organ damage. The disease affects millions of people in tropical and subtropical regions and is spreading as climate change expands sandfly habitat. The control of vector-borne diseases requires understanding not just the pathogen, but also the vector's biology, behavior, and ecology. It requires integrated approaches that combine environmental management, chemical control, personal protection, and sometimes novel technologies like genetically modified mosquitoes. The vectors have evolved alongside the diseases they carry, and controlling them requires matching their evolutionary adaptability with our own ingenuity. Some diseases have not been defeated but have been managed into a kind of coexistence. Medical advances have transformed them from death sentences into chronic conditions that people can live with, sometimes for decades. HIV remains incurable, but treatment has transformed it dramatically. People with HIV who take antiretroviral therapy can expect near-normal lifespans. They can have children without transmitting the virus. They can live full lives, the disease managed if not eliminated. The key is early diagnosis and consistent treatment. When these are available, HIV is no longer the death sentence it once was. This transformation required decades of research, billions of dollars, and the activism of affected communities who demanded that their lives be treated as worth saving. The HIV story is one of science and activism working together, of treatment that seemed impossible becoming reality, of a disease that terrified the world becoming manageable. But HIV remains a challenge. Treatment must be taken daily for life. Drug resistance can develop if treatment is inconsistent. Access to treatment is still limited in many parts of the world, and prevention remains imperfect. No vaccine exists, and behavior change is difficult to sustain. HIV continues to infect millions each year, even as those already infected live longer and healthier lives. Tuberculosis remains a major killer, but treatment can cure most cases. The challenge is reaching everyone who needs treatment, providing the months of medication required for cure, and preventing the emergence of drug-resistant strains. Tuberculosis kills more people than any other infectious disease, but the deaths are preventable with adequate investment in health systems. The treatment of tuberculosis requires months of daily medication, a regimen that is difficult for patients to maintain. If treatment is stopped too soon or taken inconsistently, the bacteria can develop resistance. Drug-resistant TB is much harder and more expensive to treat, and extensively drug-resistant TB is sometimes incurable. The emergence of resistance is a constant threat, driven by inadequate treatment programs and inconsistent medication. Diabetes, while not infectious, has become a disease that millions live with. The condition cannot be cured, but it can be managed through medication, diet, and lifestyle changes. People with well-controlled diabetes can live long, healthy lives, but poorly controlled diabetes leads to heart disease, kidney failure, blindness, and amputations. The disease requires constant attention and management. Chronic hepatitis B and C affect hundreds of millions of people. Hepatitis B can be controlled with antiviral medications that suppress the virus, though they rarely eliminate it entirely. Hepatitis C can now be cured with antiviral drugs that eliminate the virus in most patients, though treatment remains expensive and inaccessible for many. Both diseases can lead to liver cancer and cirrhosis if untreated. Epilepsy, autoimmune diseases, and many other chronic conditions require lifelong management. They cannot be cured, but they can be controlled, allowing people to live relatively normal lives. The boundary between health and disease blurs when disease becomes a condition to be managed rather than an enemy to be defeated. Living with disease is, in some sense, the normal state of humanity. Complete health is an ideal rarely achieved. Most people carry some condition, some imperfection, some vulnerability that they manage through medication, lifestyle, or simply acceptance. The diseases we live with shape our daily lives, our choices, our identities. Quarantine is one of the oldest public health measures, originating in the 14th century as a response to plague. The word comes from the Italian quarantina, meaning 40 days, the period that ships were required to anchor offshore before passengers could disembark. The practice was based on the observation that disease could be transmitted from person to person, even if the mechanism was not understood. Quarantine is a form of collective defense against disease, a recognition that the community has an interest in controlling infection that supersedes individual freedom. The power to quarantine has been controversial throughout history, raising questions about liberty, authority, and the balance between individual rights and public safety. The same questions arise with other public health measures. Vaccination, which has saved more lives than any other medical intervention, has always faced resistance from those who object to government mandating medical procedures. Water fluoridation, which prevents tooth decay, was attacked as government overreach. Mask mandates during respiratory epidemics have sparked protests and political conflicts. These controversies reflect the tension between individual autonomy and collective welfare that runs through democratic societies. Disease forces this tension into the open, because controlling infectious disease requires collective action. One person's choice not to vaccinate affects not just themselves but everyone they might infect. One person's refusal to quarantine can spread disease to thousands. The history of public health is a history of expanding collective responsibility for health outcomes. Clean water, sanitation, vaccination, food safety, tobacco control, each of these achievements required society to accept limits on individual behaviour for the common good. Each faced resistance, and each eventually became accepted as part of the social contract. Disease has shaped politics and governance as much as genetics and biology. The fear of epidemics has been used to justify both necessary measures and oppressive ones. Disease has been blamed on outsiders, minorities, the poor, the different, fueling discrimination and violence. The response to disease reveals as much about societies as the disease itself. Every culture has explanations for disease. Before germ theory, before microscopes, before scientific medicine, people sought to understand why illness struck, why some died and others lived, why suffering existed in the world. The answers they found shaped religions, philosophies, and social structures. Many cultures attributed disease to supernatural causes. Illness was punishment from gods, the work of demons, the result of curses or broken taboos. These explanations provided meaning and structure to the chaos of epidemics. If disease was punishment, it could be avoided through proper behaviour. If disease was caused by spirits, it could be fought with rituals and prayers. The explanations, however inaccurate scientifically, gave people a sense of understanding and control. These supernatural explanations shaped behaviour in ways that sometimes helped and sometimes harmed. Avoiding the sick, which many cultures practiced, could reduce transmission. But attributing disease to sin could lead to blaming and persecuting victims, as happened during the plague when Jews were massacred based on accusations of poisoning wells. The meanings humans gave to disease had real consequences. Religious practices often incorporated responses to disease. Ritual cleanliness, prescribed in many religions, may have originated as disease prevention measures encoded in religious law. Dietary restrictions, like the prohibition of pork in Judaism and Islam, may have protected against parasites common in pork. The boundaries that religions drew around purity and impurity often tracked with disease transmission routes. Disease shaped religious belief itself. The experience of epidemic, of suffering, of arbitrary death, forced people to grapple with questions of meaning and justice. Why do the innocent suffer? Why does God permit plague? These questions shaped theology, philosophy, and the human search for meaning. The problem of evil, central to religious thought, is partly the problem of disease. The Black Death transformed European culture. The massive mortality, the randomness of who survived and who died, the failure of prayers and medicine to stop the plague, all of these challenged existing beliefs and institutions. Some turned to fanatical religiosity, others to hedonism, others to despair. The art of the period, with its danse macabre motifs and its obsession with death, reflected a culture traumatized by disease. The cholera epidemics of the 19th century had similar cultural effects. The disease struck suddenly, killed quickly, and seemed to prefer the poor. It raised questions about urban poverty, about sanitation, about the responsibilities of government. The fear of cholera drove social reforms that transformed cities and improved lives for millions. HIV/AIDS transformed culture in the late 20th century. The disease raised questions about sexuality, about identity, about care for the dying. It mobilized communities, particularly the gay community, to political action. It changed how medicine is practiced, as patient advocacy groups demanded participation in research and treatment decisions. The cultural effects of AIDS extended far beyond those directly infected. COVID-19 is still too recent for its cultural effects to be fully understood, but they will be profound. The pandemic changed how people work, how they socialize, how they think about risk and community. It exposed inequalities, accelerated technological changes, and raised questions about the relationship between individuals and society. The culture that emerges from COVID-19 will be different from the culture that preceded it. The evolutionary trade-offs. Evolution does not create perfect solutions. It creates compromises, trade-offs between competing pressures. The genetic adaptations that protect against one disease may increase vulnerability to another. The immune responses that fight infection may damage healthy tissue. The genes that helped our ancestors survive may cause problems in modern environments. The sickle cell trait is the classic example. One copy of the sickle cell gene protects against malaria. 2 copies cause sickle cell disease, a serious condition that shortens life and causes chronic pain. Evolution has maintained this harmful gene because, in malaria endemic regions, the benefit of protection outweighs the cost of disease. The math is brutal. Enough people with 1 copy survive malaria to make the gene worthwhile, even though some people with 2 copies suffer and die. Similar trade-offs exist throughout the human genome. The genes that protected against plague may increase the risk of autoimmune diseases. The gene variants that help fight tuberculosis may contribute to inflammatory conditions. The immune system itself is a balance between aggression and restraint, between attacking invaders and tolerating self. Tilt too far in either direction, and the result is disease, either vulnerability to infection or autoimmune destruction. The cystic fibrosis gene may persist, because carriers have some resistance to cholera or typhoid. The gene causes a serious lung disease in those who inherit 2 copies, but the carrier advantage may be enough to maintain it in the population. The evidence is not conclusive, but the pattern is consistent with what we see for other disease-resistance genes. These trade-offs explain why harmful genes persist in human populations. Natural selection cannot eliminate a gene if it provides benefits that outweigh its costs, even if those costs are substantial. The result is a genome littered with compromises, with genes that cause harm in some contexts while providing benefit in others. The modern environment has changed many of these trade-offs. Malaria is less common than it once was. The benefit of sickle cell protection is reduced while the cost of sickle cell disease remains. Cholera is rare in developed countries. Any benefit of cystic fibrosis carrier status is irrelevant while the disease itself persists. We carry genes adapted to ancestral environments that no longer exist. This mismatch between our genes and our environment may explain some modern diseases. The thrifty genes that helped our ancestors survive famines may contribute to obesity and diabetes in environments of abundance. The immune responses that evolved to fight parasites may cause allergies and asthma when those parasites are absent. We are adapted to a world that no longer exists, and the consequences show in our health. Understanding these trade-offs is crucial for medicine and public health. Gene therapy might eliminate sickle cell disease, but the same genetic variant provides protection that some populations still need. Suppressing inflammation might help autoimmune diseases, but might also impair defense against infection. Every intervention has consequences, and the evolutionary history that shaped our genes must be considered. Disease shapes not just our bodies, but our minds. The fear of contagion, the disgust at signs of infection, the tendency to avoid the sick. These psychological responses evolved because they helped our ancestors survive. They are part of our evolutionary inheritance as much as our immune systems. The behavioral immune system is the term psychologists use for the psychological defenses against disease. We feel disgust at things that might harbour pathogens, spoiled food, bodily fluids, signs of infection. We avoid people who appear sick, keep our distance, wash our hands after contact. These behaviours reduce our risk of infection, complementing the biological immune system that fights pathogens that get through. This behavioural immune system can be triggered by cues that merely suggest infection, even when no actual pathogen is present. Unusual appearances, unfamiliar smells, foreign customs, all can activate disgust and avoidance responses that evolved to protect against disease but that now sometimes manifest as prejudice. Studies have shown that disease concerns can increase negative attitudes toward outgroups, perhaps because unfamiliar people were once more likely to carry unfamiliar pathogens. The psychological impact of epidemics extends beyond individual behaviour. Societies respond to disease threats with collective measures that can range from helpful to harmful. Quarantine and isolation protect the healthy, but stigmatise the sick. The search for explanations can lead to scapegoating, as happened during the Black Death when Jews were blamed for poisoning wells. Fear of disease can tear social bonds or strengthen them, depending on how the fear is channeled. The trauma of epidemics persists long after the disease itself is controlled. Survivors of serious illness often experience psychological effects including depression, anxiety, and post-traumatic stress. Communities that have experienced mass mortality carry collective trauma that shapes culture and behavior for generations. The psychological scars of disease may outlast the physical ones. Modern psychology has begun to address the mental health aspects of infectious disease. The COVID-19 pandemic brought unprecedented attention to the psychological impacts of illness, isolation, and fear. Healthcare workers experienced burnout and trauma. Patients and families faced grief and loss. The recognition that disease affects mental health as well as physical health is an important advance in how we understand and respond to epidemics. Human existence is an ongoing experiment in survival. Every generation faces new challenges, new diseases, new selective pressures. The experiment has no endpoint, no final exam, no graduation. It continues as long as humans exist, as long as pathogens evolve, as long as the conditions of life keep changing. We are in the middle of this experiment right now. The diseases we face today are different from those our grandparents faced, and our grandchildren will face diseases we cannot predict. Some will be old enemies returning, tuberculosis developing new resistance, measles surging when vaccination falters. Some will be new threats emerging from the endless creativity of microbial evolution. The choices we make now will shape the experiment for generations to come. Investment in research develops tools to fight future diseases. Strong public health systems can detect and contain outbreaks before they become pandemics. Equitable access to healthcare means that resistance does not develop in undertreated populations. The experiment's outcome depends on what we do. Climate change is already altering the landscape of disease. Mosquitoes are expanding their range, bringing tropical diseases to temperate regions. Warming oceans harbour new strains of cholera. Melting permafrost releases microbes that have been frozen for thousands of years. The disease ecology of the future will be different from the past, and we are only beginning to understand how. Urbanization concentrates populations in ways that favour epidemic spread. More than half the world's population now lives in cities, in densities that allow diseases to spread rapidly. The megacities of the developing world, with their crowded slums and inadequate infrastructure, are potential breeding grounds for the next pandemic. Global travel connects every part of the world in ways that allow diseases to spread faster than ever before. A virus can travel from one continent to another in a day, carried by an infected traveller who may not even know they are sick. The connected world is a vulnerable world, where an outbreak anywhere is a threat everywhere. But global connection also enables rapid response. Information about new diseases spreads as fast as the diseases themselves. Genome sequences can be shared instantly, allowing researchers worldwide to begin working on diagnostics, treatments, and vaccines. The same connectivity that spreads disease also spreads knowledge. The ongoing experiment will continue. New diseases will emerge. Old diseases will return. The balance of power between humans and microbes will shift, sometimes in our favour, sometimes in theirs. The outcome is not predetermined. It depends on the choices we make, the investments we prioritise, the vigilance we maintain. Edward Jenner, an English physician, developed the first vaccine in 1796, demonstrating that inoculation with cowpox could protect against smallpox. His work laid the foundation for immunisation, the most effective disease prevention tool ever developed. Jenner faced scepticism and ridicule, but his discovery ultimately saved more lives than any other single medical advance. Louis Pasteur and Robert Koch established the germ theory of disease in the 19th century, proving that microorganisms caused infections. This understanding transformed medicine, making possible antiseptic surgery, water purification, food safety, and targeted treatments for specific diseases. Before germ theory, doctors often did more harm than good. After it, medicine became a science. Alexander Fleming discovered penicillin in 1928, inaugurating the antibiotic era. Infections that had killed for millennia became curable with a course of pills. Fleming's discovery and the subsequent development of other antibiotics changed what was possible in medicine, allowing surgeries and cancer treatments that would otherwise be too dangerous. Jonas Salk and Albert Sabin developed the polio vaccines that have nearly eradicated a disease that once paralyzed thousands of children each year. Salk famously refused to patent his vaccine, saying it belonged to the people. His generosity and commitment exemplified the idealism of mid-20th century public health. Countless others have contributed to the fight against disease: the epidemiologists who track outbreaks, the researchers who study pathogens, the doctors who treat patients, the public health workers who implement prevention programs. Most are unknown to history, but their collective efforts have transformed human life, reducing mortality from infectious disease by orders of magnitude. These heroes faced the diseases that shaped humanity and fought back. They turned the relationship between humans and disease from one of passive suffering to active combat. They gave humanity tools to shape its own biological destiny, to resist the selective pressures that had previously been beyond our control. But the fight is not won. New diseases emerge. Old diseases evolve resistance. The relationship between humans and pathogens continues to evolve, and the outcome remains uncertain. The heroes of the past have given us advantages, but the future depends on the heroes of the present and future continuing the fight. Smallpox is gone. The disease that killed more humans than any other, that scarred survivors for life, that devastated entire continents, exists now only in 2 laboratory freezers. The last natural case was in 1977. The eradication was achieved through global cooperation, through vaccination campaigns that reached the most remote villages, through surveillance and containment that tracked down and eliminated the last cases. The eradication of smallpox is one of humanity's greatest achievements. It required decades of effort, billions of dollars, the commitment of governments and health workers worldwide. It succeeded because smallpox had characteristics that made eradication possible. The vaccine was effective. The disease had no animal reservoir, cases were visible and could be identified and contained. Polio is almost gone. The disease that paralyzed thousands of children each year, that filled hospitals with iron lungs, that terrified parents every summer, has been reduced to just a few cases in a few countries. 2 of the 3 wild poliovirus strains have been eradicated. The eradication campaign continues, fighting against remaining pockets and against vaccine-derived strains that have emerged. The success against polio demonstrates what is possible when resources and will are aligned. But it also demonstrates how difficult the final stages of eradication can be. The last cases are often in the hardest to reach places, the most conflict-affected areas, the communities most suspicious of outside intervention. Finishing the job requires patience and persistence that must be sustained for years. Guinea worm disease is nearly eradicated, reduced from millions of cases in the 1980s to just a handful today. This parasitic disease, caused by worms that grow under the skin and emerge painfully through blisters, has been controlled through simple measures: filtering drinking water, educating communities, containing cases. No vaccine or drug is needed. Behavior change alone can eliminate the disease. Measles deaths have declined by more than 95% since vaccination became widespread. Whooping cough, diphtheria, tetanus, all have been brought under control through vaccination. Diseases that once killed millions of children each year now kill only thousands, mostly in places where vaccination coverage is low. These victories show that humans can win against disease, that the relationship of prey and predator can be reversed. The diseases that shaped humanity can be brought under control, their evolutionary pressure reduced or eliminated. We are not passive subjects of microbial selection. We can fight back, and we can win. But victory requires vigilance. Diseases that have been controlled can return if prevention efforts weaken. Measles outbreaks occur when vaccination rates fall. Polio can spread again if eradication falters. The diseases we have defeated are not dead. They are only contained, waiting for the opportunity to return. The relationship between humans and disease is changing faster than ever. Medical science can now edit genes, design vaccines in days, and monitor outbreaks in real time. The tools available to fight disease are more powerful than anything our ancestors could have imagined. But the threats are also changing. Climate change is altering the distribution of disease vectors, allowing tropical diseases to spread to new regions. Urbanization concentrates populations in ways that favor epidemic spread. Global travel means that a disease can move from emergence to pandemic in weeks. Antibiotic resistance threatens to return us to a pre-antibiotic era of untreatable infections. The COVID-19 pandemic revealed both the power of modern medicine and its limitations. Vaccines were developed with unprecedented speed, but their distribution was uneven. Public health measures worked, but they were politically contested. The pandemic was eventually controlled, but not before millions died. The response showed what humanity can do when mobilized, but also how far we have yet to go. Future pandemics are inevitable. The question is not whether they will occur, but how severe they will be and how well we will respond. Preparation now, investment in surveillance and research and public health infrastructure, can reduce the toll of future outbreaks. Neglect now will be paid for in lives later. Gene editing technologies like CRISPR raise new possibilities for fighting disease. We may be able to eliminate genetic diseases, modify human genes to provide resistance to infections, even edit disease vectors to make them harmless. These technologies are powerful, but also raise profound ethical questions about what it means to reshape the human genome. The eradication of more diseases is now within reach. Polio is close. Guinea worm is closer. Other diseases are being targeted for elimination. The dream of a world without the diseases that have shaped humanity for millennia is no longer fantasy but a realistic goal. But elimination is difficult, and some diseases may never be eradicated. Malaria, tuberculosis, HIV, these have proven resistant to elimination efforts, persisting despite massive investments. The diseases that remain are often the hardest to eliminate, protected by complex biology or social conditions that make control difficult. The human microbiome is a new frontier in understanding health and disease. As we learn more about the trillions of microorganisms that live within us, we may find new ways to prevent and treat disease. Probiotics, fecal transplants, microbiome engineering, these approaches are in their infancy, but hold promise for addressing conditions from infection to autoimmune disease. The future of disease and humanity is being written now. The choices we make about research, about preparation, about equity and healthcare access will shape how disease affects future generations. We have more power than any previous generation to control our relationship with the microbial world. Whether we use that power wisely remains to be seen. For every disease that has shaped humanity, countless others have been prevented from doing so. The pathogens that could have devastated our species but did not, stopped by geographic barriers, by immune defenses, by medical intervention, by luck, are invisible in the historical record. We know only the diseases that succeeded in spreading. Those that failed leave no trace. Consider the pathogens that remain confined to their animal hosts. There are viruses circulating in bats, in rodents, in primates that could potentially infect humans but have not made the jump. Each represents a possible pandemic that has not happened, yet. The barriers between species are not absolute. They can be crossed when conditions are right. Every zoonotic disease that has devastated humanity, HIV, SARS, COVID-19, was once confined to animals until circumstances allowed it to spread to humans. Consider the outbreaks that were contained before they could become epidemics. Public health surveillance detects hundreds of potential disease emergencies each year. Most are controlled through rapid response, isolation of cases, treatment of the sick, vaccination of the vulnerable. These successes are invisible precisely because they succeeded. The pandemic that did not happen is not a story that gets told. Consider the diseases that vaccines have prevented from spreading. Every child vaccinated against measles is a child who will not spread the virus to others. Every outbreak prevented is an epidemic that did not occur, a selective pressure that was never applied, a shaping that did not happen. Vaccination has removed entire diseases from the list of forces acting on human populations. The children who are never born because their potential parents died of disease are invisible too. The genetic combinations that were never tested because their carriers died before reproducing. The adaptations that might have emerged but never did. All of these are part of the shadow history of disease and humanity. The paths not taken, the shapes that were never formed. This shadow history reminds us that what exists is not inevitable. Human evolution could have taken different paths if different diseases had emerged or spread. The genetic adaptations we carry reflect the diseases that shaped us, but they are not the only adaptations possible. In a different disease environment, we would be different people. It also reminds us that the future is not determined. The diseases that will shape humanity tomorrow do not yet exist, or exist but have not yet spread. Our choices about research, about surveillance, about equity, about environmental change will determine which potential diseases become actual diseases, which outbreaks become pandemics, which pathogens get the opportunity to shape human evolution. The diseases that shaped humanity are not finished shaping, but neither are we finished shaping them. The relationship is mutual, dynamic, and ongoing. What comes next depends on both sides of the evolutionary equation. Your bone marrow is producing white blood cells right now, the soldiers of your immune system. B cells are forming, each with a unique receptor capable of recognizing a specific pathogen. T cells are maturing, learning to distinguish self from non-self, preparing to coordinate the immune response if needed. These cells will patrol your body for weeks or months, watching for invaders. In your lymph nodes, immune cells are meeting, exchanging information, responding to any threats they have detected. The lymph nodes are where immune responses are organized, where B cells receive the signals to produce antibodies, where T cells are activated to seek and destroy infected cells. This machinery runs constantly, maintaining surveillance even when you feel perfectly healthy. Antibodies are circulating in your blood, proteins that your immune system produced in response to past infections or vaccinations. Each antibody can recognize a specific pathogen, binding to it and marking it for destruction. You carry antibodies against diseases you had as a child, against vaccines you received, against infections you may not even remember having. Memory cells are dormant throughout your body, waiting. These cells remember past infections and can respond rapidly if the same pathogen returns. They are the basis of long-term immunity, the reason why you can only get measles once, why vaccination provides lasting protection. These memory cells are a living archive of your immune history. Your skin, that largest organ, is a barrier against the microbial world, constantly renewing itself, shedding cells that might carry pathogens, hosting communities of beneficial bacteria that crowd out harmful ones. Your mucous membranes trap invaders and propel them out of your body. Your stomach acid destroys pathogens in food. These defenses operate without your awareness, the first lines of defense that most invaders never get past. All of this machinery is the product of evolution, refined over hundreds of millions of years of conflict between hosts and pathogens. Your body carries the lessons of every disease your lineage ever faced, encoded in genes and expressed in proteins that work to keep you alive. You carry within you the accumulated wisdom of evolution, tested and refined by millennia of disease. Imagine a virus particle, smaller than a wavelength of light, landing on the membrane of one of your cells. The virus has proteins on its surface that fit receptors on your cell like a key in a lock. The virus attaches, and the cell, not recognizing the threat, draws the virus inside. This is the moment of infection. The breach in your defenses, the beginning of the battle. Inside the cell, the virus hijacks the cellular machinery. It uses your ribosomes to build viral proteins, your enzymes to replicate its genetic material, your membranes to assemble new virus particles. The cell becomes a factory for the invader, producing thousands of new viruses that will burst out and infect other cells. But your defenses are not passive. The infected cell recognizes that something is wrong. Viral proteins inside the cell trigger alarm systems that have evolved over millions of years. The cell begins to display pieces of the virus on its surface, like waving a flag to alert the immune system. It releases signaling molecules that summon help. It may even commit suicide, destroying itself to prevent the virus from using it further. The innate immune system responds first. Macrophages, cells that engulf and destroy invaders, arrive at the site of infection. They consume virus particles and infected cells, working to contain the invasion. Natural killer cells attack infected cells directly, punching holes in their membranes and triggering their death. Inflammation begins, causing the redness, heat, and swelling that signal an active immune response. Meanwhile, the adaptive immune system is activating. Pieces of the virus carried by specialized cells to the lymph nodes are presented to T cells and B cells. The cells whose receptors happen to match the virus begin to multiply, creating armies of pathogen-specific fighters. This process takes days, which is why you feel sick before you feel better, the innate immune system holding the line while the adaptive system mobilizes. B cells produce antibodies, proteins that circulate through the bloodstream and bind to virus particles, marking them for destruction and preventing them from entering cells. T cells, once activated, either kill infected cells directly or coordinate the response, directing other immune cells where they are needed. The adaptive response is specific and powerful, usually capable of clearing the infection within a week or two. When the virus is defeated, most of the immune cells die, their job done. But some become memory cells, persisting in the body for years or decades, ready to respond instantly if the same virus returns. This is acquired immunity, the reason why you rarely get the same infection twice, the basis of vaccination. All of this is happening inside you, has happened many times, will happen again. Every infection is a battle, fought with weapons evolved over millions of years, refined by the diseases that shaped humanity. The fact that you rarely notice that most infections are cleared without serious illness is testimony to how effective these defenses are. When you have an infection, your body temperature rises. This is not a malfunction. It is a deliberate response, controlled by the hypothalamus in response to signals from the immune system. Fever is uncomfortable, even dangerous at extreme levels, but it serves a purpose. It makes your body a less hospitable environment for pathogens. Many bacteria and viruses reproduce best at normal body temperature. Raise the temperature a few degrees, and their reproduction slows. Your immune cells, by contrast, work better at elevated temperatures. They move faster, respond more effectively, clear infections more quickly. Fever tilts the balance in favor of the host and against the pathogen. This defense is ancient. Even cold-blooded animals develop fever, seeking out warmer environments when infected, raising their body temperature through behavior when they cannot do it through metabolism. Fever evolved early in the history of animals and has been conserved because it works. The diseases that shaped humanity shaped fever too, refining it through millions of generations of host-pathogen conflict. We often suppress fever with medications, wanting to feel better, wanting to function normally. This is understandable, but it may not always be wise. Studies suggest that treating mild fevers can actually prolong illness because the treatment removes a defense that was helping to fight the infection. The discomfort of fever is the price of a more rapid recovery. Of course, extreme fevers are dangerous and should be treated. The defense can become a threat if the temperature rises too high, but mild to moderate fevers are generally beneficial, part of the sophisticated response that evolution has developed to combat disease. When tissue is damaged or infected, the area becomes inflamed, red, hot, swollen, painful. These symptoms are not the disease, they are the response to the disease, part of the immune system's effort to contain and eliminate the threat. The redness comes from increased blood flow to the area, bringing immune cells and nutrients needed for repair. The heat comes from the same increased blood flow and from the metabolic activity of immune cells working hard. The swelling comes from fluid leaking from blood vessels into the tissue, diluting toxins and delivering antibodies. The pain comes from signals that tell you to protect the affected area, to rest, to let healing happen. Inflammation evolved because it helps. It concentrates immune resources at the site of infection. It creates an environment hostile to pathogens. It begins the process of repair. But inflammation can become a problem when it's excessive or chronic. The same response that fights infection can damage healthy tissue if not properly controlled. Autoimmune diseases, where the immune system attacks the body's own cells, often involve inappropriate inflammation. The genes that control inflammation have been shaped by disease, and they reflect trade-offs between effective defense and dangerous overreaction. Some of the genes that make autoimmune diseases more likely may have been selected because they provided better protection against infections. The increased risk of rheumatoid arthritis or Crohn's disease may be the price paid for more effective immune responses. Sleep is essential for immune function. During sleep, your body produces and deploys immune cells, consolidates immune memory, and carries out maintenance processes that are suppressed during waking hours. People who sleep poorly get sick more often, recover more slowly, and respond less effectively to vaccines. Sleep is not just rest, it is an active process essential for health. The diseases that shaped humanity selected for good sleepers. Those who slept well had stronger immune systems, survived infections better, recovered faster. Sleep patterns are partly genetic, and the genes that influence sleep have been shaped by the same selective pressures that shaped immune genes. Your need for sleep, your ability to sleep, your pattern of sleep, all reflect evolutionary adaptations to a world of disease. As you drift towards sleep tonight, you're doing something that helps keep you healthy. You're allowing your immune system to do maintenance it cannot do while you are awake. You're consolidating the immune memories that will protect you in the future. You're supporting the processes that connect sleep, to the long history of your species' battle with disease, consider the numbers that are almost too large to comprehend. Malaria has killed an estimated half of all humans who ever lived. Think about that. Half of all the people who have ever existed, billions upon billions of individuals across hundreds of thousands of years, died from this single disease. The malaria parasite has been more successful at killing humans than all wars combined, than all famines, than all natural disasters. Smallpox killed an estimated 300 to 500 million people in the 20th century alone before it was eradicated. The plague of Justinian killed perhaps 50 million. The Black Death killed perhaps 200 million. The 1918 flu killed 50 to 100 million. These are not statistics. They are people, each one as real as you, each with a life that was cut short by disease. The scale of suffering is impossible to truly grasp. Every one of those deaths involved pain, fear, grief. Families were torn apart, communities were devastated, dreams were ended. The diseases that shaped humanity did so through unimaginable suffering, repeated generation after generation in every part of the world. And yet, life continued. Populations recovered. Humans survived. The very fact that you exist, that there are 8 billion humans on Earth today, proves that disease could not stop us. We are more numerous, more widespread, more dominant than ever. The diseases that killed billions could not prevent our species from flourishing. This resilience is itself a product of disease. The selective pressure that killed the vulnerable left the resistant. The genetic adaptations that spread through surviving populations made future generations more resilient. The medical knowledge we developed, born from the desperate need to combat epidemics, gave us tools to fight back. Disease tried to destroy us and instead made us stronger. In wealthy countries today, children rarely die from infectious disease. The diseases that filled graveyards with small bodies a century ago, measles and whooping cough and diphtheria and polio, are prevented by vaccines or treated with medicine. Parents today worry about many things, but they rarely worry that their child will be struck down by epidemic disease. This is unprecedented in human history. For hundreds of thousands of years, parents buried children. It was normal, expected, a tragedy so common that it hardly needed mentioning. To reach adulthood was an achievement. To see all your children reach adulthood was rare. Today's children do not know that world. They do not remember iron lungs, do not know what it means to be quarantined for scarlet fever, have never seen a sibling die of dysentery. The diseases that shaped humanity are, for them, stories in history books, not present threats. This is a victory, perhaps the greatest victory humanity has ever won. We have given our children something that our ancestors could only dream of, a reasonable expectation of survival, a childhood not shadowed by the constant threat of epidemic death. The diseases that shaped humanity have been pushed back, their power diminished, their toll reduced. But this victory is fragile. The diseases are not gone, they are controlled. If vaccination rates fall, measles will return. If surveillance lapses, new diseases will spread unchecked. If antibiotic resistance continues to grow, infections once again will kill. The children who do not know what we knew must still maintain the defences that their safety depends upon. Health is not just the absence of disease. It is an active process, a dynamic balance maintained by countless systems working together. Your immune system fights off the microbes that constantly try to colonize you. Your liver detoxifies the substances that could harm you. Your kidneys filter your blood, removing waste and maintaining balance. Your cells repair damage, divide to replace what is lost, coordinate to maintain the whole. This maintenance happens without your awareness, without your direction, without your gratitude. You do not thank your macrophages for consuming bacteria, do not appreciate your B cells for producing antibodies, do not notice your epithelial cells shedding and regenerating. The work is invisible, and health feels like nothing, like the default state, like something to be expected. But health is not nothing. Health is the result of work, of systems that evolved under intense selective pressure, of defences that were tested and refined by the diseases that shaped humanity. Every moment of health is a moment of victory in the endless war between you and the microbial world. The diseases that shaped humanity created health. Without disease, there would be no immune system, no repair mechanisms, no sophisticated defences. Health exists because disease exists. Because surviving disease required health. Because the healthier survived to pass on their genes. Health and disease are not opposites. They are partners in a co-evolutionary dance that has no end. Tonight, you are healthy. Your defenses are working. Your body is maintaining its balance. This is not nothing. This is everything. This is what your ancestors survived to give you, what evolution refined over billions of years, what medicine has enhanced and protected. Your ancestors survived. They faced diseases without antibiotics, without vaccines, without understanding of how infections spread. They survived through luck and genetics and the immune systems that evolution had given them. Many died, but enough survived to continue the line that led to you. You owe them your existence. The scientist who unraveled the mysteries of disease gave us tools our ancestors could not have imagined. Jenner with his vaccine, Pasteur with germ theory, Fleming with penicillin, Salk with the polio vaccine, and thousands of others whose names we do not know. They fought the diseases that shaped humanity with knowledge and ingenuity, and they won battles that generations before had lost. The public health workers who implement what the scientists discovered deserve gratitude too. The nurses who vaccinate children, the epidemiologists who track outbreaks, the sanitarians who ensure clean water, the countless workers who maintain the systems that keep disease at bay. Their work is often invisible, noticed only when it fails, but it is essential, and circumstances matter. You were born in a time and place where the worst diseases have been controlled. This was not your doing, it was fortune. Others, born in different places or different times, faced threats you will never know. The gratitude we feel for our safety should include humility, recognition that we did not earn what we have been given. Your gut contains more bacteria than your body has human cells. These bacteria digest food you cannot digest yourself, produce vitamins you cannot synthesize, train your immune system to respond appropriately. They are not invaders. They are partners, co-evolved over millions of years to live within human bodies. This microbiome is a community, with different species occupying different niches, competing and cooperating, maintaining a balance that is healthy when stable and problematic when disrupted. Disease disrupts this balance. Antibiotics, which kill bacteria indiscriminately, can devastate beneficial populations along with harmful ones. Recovery from infection involves not just eliminating the pathogen, but restoring the microbial community. As you rest tonight, your gut bacteria continue their work, digesting the remnants of your last meal, producing metabolites that affect your health and even your mood. They are part of you, these trillions of tiny organisms, more closely related to the bacteria that cause disease than to your own human cells. The boundary between you and the microbial world is blurrier than it might seem. The microscopic world surrounds you always, invisible and ever-present. Bacteria float in the air, settle on surfaces, colonize every inch of your body's exterior. Viruses drift on droplets, waiting for hosts, seeking cells to invade. Fungi spread their spores, parasites seek their targets. The microbial world teems with life-seeking opportunity, and you persist. Your defenses hold the line. Your immune system knows its job. You have been shaped to survive exactly this, exactly what surrounds you now, exactly what you face every moment of every day. Tonight that work continues, but you need not be aware of it. Your body knows what to do. Sleep and let it work. Tomorrow you will wake, healthy, restored, ready for another day in the endless dance between humans and microbes. You are the product of disease. Your genes were shaped by malaria, by plague, by smallpox, by all the infections that killed your ancestors who lacked resistance and spared those who had it. Your immune system is a weapon forged in evolutionary warfare, refined by millions of years of battle against pathogens. Your very existence is proof that your lineage found ways to survive what killed so many others. This inheritance is not passive. It is active, working within you right now. As you lie here in the darkness, your immune system is patrolling your body, identifying and eliminating threats, remembering past invaders, preparing for future ones. You are protected by the accumulated wisdom of evolution, the genetic knowledge of how to survive in a world of microbes. The diseases that shaped humanity are still with us, though their power has been diminished. We have vaccines and antibiotics, sanitation and medicine, tools that our ancestors could not have imagined. We have transformed the relationship between humans and disease, shifting from prey to something closer to equals in the endless evolutionary struggle. But humility is appropriate. The microbial world is vast and creative. New diseases emerge, old diseases evolve, and the balance of power is never fixed. The victories we have won can be reversed if we're not vigilant. The future is not determined. It depends on choices we make and actions we take. The story of disease and humanity is not over. It continues with every infection, every immune response, every mutation in a pathogen or a host. It continues in laboratories where researchers study pathogens, in clinics where doctors treat patients, in communities where public health workers implement prevention programs. It continues in you, in your genes, and your microbiome and your immune system, all shaped by diseases past and present. The night around you is peaceful, but it is not empty. Microbes are everywhere, on your skin, in your gut, in the air you breathe. Most are harmless or beneficial, partners in the symbiosis that makes your life possible. A few might be dangerous, but your immune system is vigilant, ready to respond, equipped with the lessons of 1 billion years of evolution. Tomorrow you will wake, and your body will continue its quiet work of defense and maintenance, repair and renewal. The processes that keep you healthy operate whether you're aware of them or not, a silent army working on your behalf. You do not need to direct them. They know their jobs, encoded in genes that were tested and refined over millions of generations. The stars that shine tonight have watched over billions of years of life on Earth, billions of years of the struggle between organisms and the pathogens that infect them. This struggle predates humanity, predates animals, predates anything that could be called complex. It began when the first cells encountered the first parasites, and it has never stopped. You're part of that ancient story. The cells that make up your body are descendants of cells that fought off infections billions of years ago. The immune system you carry evolved from defenses that single-celled organisms developed long before anything had eyes or brains or lungs. The war between life and disease is older than you can imagine, and you are its latest chapter. Every generation has faced this challenge. Every generation has lost members to disease and passed on survivors to the next. The chain is unbroken from the first life to you, and it will continue unbroken to your descendants and beyond. The diseases that shaped humanity are still shaping, still selecting, still pushing life to adapt or perish. The night is complete. The story is told. The body is at rest. Your ancestors faced plagues without understanding what caused them. They faced fevers without medicine to reduce them. They faced infections without antibiotics to cure them. And enough of them survived, generation after generation, to create the line that led to you. Honor them by living well. Honor them by appreciating the health they could not take for granted. Honor them by sleeping peacefully in a world they made safer through their survival. Honor them by remembering that every breath you take, every heartbeat, every moment of health is a gift purchased with their suffering and paid forward through generations of survival. For as long as there has been life, there has been disease. For as long as there has been disease, life has found ways to survive. You are proof that survival is possible, that the defenses work, that the fight can be won, at least for now, at least for tonight. The immune cells patrol your blood. The antibodies stand ready. The microbiome maintains its balance. The genes carry their ancient instructions. Everything that makes you able to be healthy is working right now as you drift towards sleep. This is the legacy of the diseases that shaped humanity. Not just suffering, not just death, but also the strength that emerged from survival. You are that strength made flesh, that survival continuing, that ancient victory renewed. Rest in that knowledge. Rest in that peace. Rest in that quiet triumph of being alive. The night holds you safe in its quiet embrace. The defenses protect you with vigilance honed over eons. The rest heals you, knitting together the damage of the day, strengthening the systems that keep you whole. Sleep well, carrier of ancient defenses, heir to millions of years of evolutionary wisdom. Sleep well, living link in the chain of life. The diseases that shaped humanity have not claimed you. You are still here, you are still breathing, you are still alive. Tomorrow the story continues as it has continued for billions of years. Tonight there is only rest, only peace, only the quiet work of healing. Good night.